we were just thinking about decision theory as it applies to supervised learning, and we found that what we wanted to do was to minimize this expected loss here. And in case 1, when we're given a particular x, we're minimizing this conditional expected loss, and we applied it to 0, 1 loss. Now that should be actually y hat. Right, we're minimizing y hat. Never mind. Okay, so that was just a detail. And now let's think back to case 2, where we want to generalize this a bit and choose a function to handle all the x's. So what happens in case 2? So let's suppose we choose, let's pick some arbitrary f and let's see what happens. So let's say we've picked some f, and let's write down, let's call maybe y hat f of x. Remember, we had defined, we were thinking about, where'd it go? Here we go. We were thinking about this x and y as being random. We're given y or an x, which we have to classify, and we want to choose a good y for that x. So let's say we have our function here f, which does the, say, classification or regression. Let's think about classification for now. And this, now we want to minimize the expected loss, and what is that? So let's write down what it is that we want to minimize. Well, it's the loss between the true y and our prediction, which is random now. And we take the expected value over all the random stuff, which is x and y. So let's write out, so we're not conditioning on any particular value of x anymore. So this, what is this y hat? Well, just by definition, that's just f of x. So we're taking the expectation over x and y. So let's make a little more room here. This, we'll just write out the expectation of this loss function. Since we're assuming these are discrete for now at least, we can just sum over all the x's and y's, and this is the loss of y with f of x times the probability that x and y take those values. And let's factor this, more space. Now let's factor this guy. Let's see, what can we do here? Let's factor this, which way we want. I think we want y given x times p of x. Yeah, that's what we want. We want to factor that. And so we're just, we just wrote down this expected loss, and we're just kind of playing with it to see what it looks like. So let's factor it this way. And then this sum is a sum over, let's put the x sum on the outside, and then we have the y sum on the inside. Loss of y with f of x. And now, so let's put this expected value with the inner sum. So we just have this. I just rewrote what the previous line was by factoring that. And let's now think about this inner sort of sum. So we just factored this out. We pulled out the p of x. And what's going on here? This is, well, let's see, this is a function of x. It doesn't depend on y because we're summing over y. So let's give that a name. Let's call that g of x. We could call it g of x. Let's call it g of x and f of x. So it takes two values. And then this whole thing we can just write as the sum over x, g of x, f of x, p of x. So this is, now we recognize the form of this type of thing. This is just an expected value with respect to the marginal distribution on x. So let me write the expected value with respect to that marginal distribution as just ex of this function, this random function. That's interesting. So we were able to rewrite this thing that we wanted to minimize in terms of this. And now let's suppose we started out with just some arbitrary f. And let's think about if we had, say, so we've got our original f and we've got g of, let's look at some particular point x. So for some x, say, so we've got this, our function is doing this thing. And let's say that that's strictly greater than g of x, I don't know, t, for some t. So for some, so this is for some, so suppose for some x and t, this holds. Well, if that were true, then we could define a new function. We could define, say, f0 of x to be equal to f of x. Well, let's call this a particular x. Let's call this, I don't know, x prime. So this is for some x prime. So we'll make f of 0 of x, f sub 0 of x, equal to f of x if x is not equal to x prime, and we'll make it t if x equals x prime. So we get our new function f0. And now this, because this is less, or maybe let's just say less or equal for now, then this, the g on using our original f, is greater or equal, because the expectation is order preserving. And so, so with our new f, our f0, we have that for all x, g of x and f of x is greater or equal to, I guess I could keep this as, let's keep that as strictly greater. And then we have the following implication that implies that for all x, we get this is greater or equal to f of 0, because it's equal whenever x is not equal to x prime and it's t otherwise. So this is greater or equal to the expected value for f0. So let's go ahead and just choose some f. So this suggests that let's just choose, so we should choose f to be, to have just the minimum of this g thing. So choose f to minimize g x with f of x. Right, so we want to choose, so let's define f of x. So now, before we started with some arbitrary f, and now we're going to define. So we should define or choose f of x to be the value of, let's see, what do we want? We want it to be the argmin over these t's of this thing, of g, x, and t. That was what we were doing here. We were finding that we could always improve f if we found some t like this. So let's just go ahead and define it. We'll just define it to be the value of t that minimizes that quantity. And then we get, so let's call that maybe, I don't know, let's call it f star, since we already had an f. So that means that this whole thing here is going to be greater or equal to this expected value for f star of x. So this is the best possible f that we could choose, this f star. So we found that to minimize, to solve this minimization problem for the case of the general case where we have to choose some arbitrary function f for all x's, what we ended up doing was just it specializes to the first case, right? Because this was the g of x that we're trying to minimize. Here we're taking the argument of this g of x and t thing, and that's just this, which if we think back to the case number 1, that's just exactly the same thing that we were minimizing here. It was the sum over y's of the loss of y with y hat and p of y given x, and that's just exactly our g that we were minimizing. So the general case, to minimize for all x's, it just specializes to, it just says, what we find is all we have to do is choose the f to minimize the conditional expectation for each given x. So this is very nice. Remember, before we found that to minimize this, all we needed to really worry about was these conditional expectations. And so it turns out from our little analysis here that this marginal distribution on x, it doesn't really matter what it is. To solve this minimization problem, all we cared about was this inner part, right? This g of x, this didn't depend on the marginal distribution at all. So when we defined our thing here, we just minimized the inner part. And so that's a very, very interesting observation. So once again, we find even in the general case that this conditional distribution p of y given x is the key quantity. If you're familiar with your conditional expectations, then you may recognize that all we were really doing here was using the law of iterated expectations, which says, so let's write out what that says, just make the connection. Law of iterated expectations says this expected value over x and y, we can write it as the expectation with respect to the marginal of x and of the conditional expectation of this thing, y with y hat given x equals little x, well, not given x equals little x, so just of x, let's say. So this equals this, and that was all we were really doing up here in this formula when we factored that distribution. All we were really doing was rewriting the expectation in this way, and this is called the law of iterated expectations. And so we just were minimizing this inner part. So that's a very nice observation.